Good morning, Jamina. Our presentation title is Smart Garbage Collection System. Our group member is Julia Chen, Gavin Xian, Yap Jenkin, and K7. So I'm going to present the breakout study, history, and future trend, and also the problem statement of this system. So the breakout of Smart Garbage Collection System. The Smart Garbage Collection System is a specially designed approach to dispose of the garbage effectively that solve the social problem of hygiene in the country. As a result, appropriate smart garbage management should be a top concern to discreet the pollution and protect the public health. The technique is far more user-friendly compared to traditional garbage management system. So next is history of smart garbage collection system. In traditional garbage system, need workers to collect the garbage one home by one home. The workers are involved all the process of garbage collections until the final disposal. The smart system region developed in the country is China. Their government released the zero waste plan and also to plan to ban the using plastic bag in the year 2022. So next is future trend of the garbage collection system. First, future trend is no more regular garbage bin and everything will turn to self-service kiosk. The waste will need the people to self-collect and recycle themselves. And the next one is no more garbage truck collect garbage one by one house. The underground waste collection system will replace it. The underground waste system can help government or the country to save the budget on purchasing truck and the petrol used by the trucks. And the last one is recycling or for garbage will fully automated. As the technology improve all the time, the AI become the more mature, so there will no need the worker to separate what need to be recycling. And the next one is problem statement. The garbage collection system in efficient in Danish house student hostel. Each garbage bin is only picked up by employee once per week, even though the bin is already full for a few days. Most students are forced to put the trucks outside of the garbage bin since the bins are always full. This will cause the hygiene problem and the healthy problem for the students. Okay, that's all for me. I will pass to the next presenter, Jenkin.
So right now I'm going to discuss about our system objective and system solution. The first system objective is that our garbage bin can use the machine learning model to actually internally classify and sort the trash items into partitions. And the second system objective is that we can actually inform the garbage workers on the current field level of the bins so that they would not need to manually check by themselves. And the third objective is that our system can also send the field level telemetry for the business stakeholder to perform analytics so that they can use the insights generated to actually further optimize the garbage collection process. So you can pause the video to take a look on our architecture diagram. We actually are gonna split our diagram into three parts. So for the first part, we actually use all of these services in the diagram to satisfy the classification and the trash sorting. Okay, like later we're gonna discuss more in the demo. Okay, and for the next diagram, we're also going to use all of these services in the diagram to actually inform the field level of the bins every single hour. And finally, for the third diagram, right, we actually also use all of these services to actually send the field level data for analytics every single day. So right now I'm gonna pass my slide to Yuan to talk about the comparison.
Thank you to my group member. So now I would like to present about 3.1 Amazon S3 versus block storage. Amazon S3 is a simple storage service. Its solution is a cloud-based object storage service that provides industry-leading scalability, data availability, security, and performance. Each item is held within a bucket. AWS 3 is a worldwide service for records, although buckets are kept in a single area. The storage class determines the object's longevity, accessibility, and cost in an S3 bucket. It uses life cycle rules to specify actions users want Amazon S3 to do during the lifespan of an item, such as migrating it to a different storage class. So the next I will present about block storage. Block storage is the Azure account give the data its namespace. Every item that users save in Azure storage has a unique account name as part of its address. S3 is a bucket for Amazon, but Azure is Azure like a directory in a file system. Block storage is a container that organizes a collection of blocks. Unstructured data is defined as data that does not adhere to any data model. Users may use Azure block storage life cycle management to transfer the data to the optimal access tier and expire that at the end of its lifespan using a rich rule-based policy. So the next I will present about 3.3 Amazon DynamoDB versus Azure Cosmos DB. The advantages for the Amazon DynamoDB is performance and scalability. These advantages can give user the ability to auto-scale the usage by tracking usage of upper bounds. It can avoid the issue of performance while reducing cost and adjustment according to usage of amount data traffic. Next is for the Azure Cosmos DB. It supports consistency levels. For instance, consistent prefix decisions and bonded stateless that allows more flexibility and low cost to performance ratio. The last that I want to present is this slide is show the difference about the Amazon DynamoDB and Azure Cosmos DB, and you can see the primary database model for Amazon DynamoDB is document store, key value store, but for the Azure Cosmos DB is document store, graph DBMS, key value store, and web column store. Then the next is the API and other access methods. For Amazon DynamoDB is HTTP API, and for the Azure Cosmos DB is document DBAP, graph API, MongoDB API, and the others. So now I will pass to the next presenter. That's all for my part. Thank you.
Okay, thank you, Yu Chen. And good day, everyone. My name is Kesavan. I'm going to present Amazon QuickSight versus Microsoft Power BI. Amazon QuickSight is a business intelligent BI solution offered by Amazon Web Services. It is powered by the SPICE Superfast Parallel in-Memory Computation Engine, and it can communicate with a variety of AWS sources, SQL databases, and other services such as Salesforce. Each user can work on the interactive analysis with multiple data sources in AWS at the same time. QuickSight provides a speedier environment as a result of this functionality. For the next slide, Microsoft Power BI is a set of analytic tools created by Microsoft. Power BI is steadfast and offers a large range of customization choices. It is able to integrate Power BI dashboards with other products is a standard feature. Overall, AWS, Amazon QuickSight, and Microsoft Power BI have become an industry standard BI tools. While Power BI is richer in features, AWS QuickSight is simple to use. Next slide is AWS IoT Greengrass core software versus Azure IoT Edge runtime. AWS IoT Greengrass core software and Azure IoT Edge runtime is installed in a device to provide the necessary support to function as a core devices. Despite the similarities, each software has a few technical differences. The first technical differences is startup and failure recovery mechanism in IoT Edge agent is less robust and efficient as compared to the Greengrass Nucleus. Greengrass Nucleus maintains the dependency graph between the components, while IoT Edge agent only maintains module startup orders using arbitrary numbers. Next slide is the second technical differences is the local communication implementation of Greengrass Nucleus is more mature than IoT Edge Hub. Azure IoT Edge MQTT broker is still in public review and soon it's going to have an expiry date. Overall, AWS is the primary choice for application development in Edge devices, followed by Azure. That's all from my part. Thank you.
So right now we're going to talk about our demo for the garbage system. So first of all, as we actually mentioned earlier, we actually require a trash classifier. So as you can see right here, we actually upload our model to the PyTorch folder. So later on, we actually use Amazon SageMaker Neo to actually compile the model. So from here, you can actually see that, first of all, the SageMaker Neo will actually get the input model from this PyTorch folder that I showed earlier, and they're actually going to output the compile model to this bucket path. So the output is actually right here. Yeah, so they actually output this tar.gz file. So after that, in order to actually install the model into the core device, we actually require two components as mentioned earlier. The first Greengrass component is the inference component, and the second Greengrass component is the model component, right? So the model component here is actually as shown right here. Yeah, so this Danish GCS trash classification model store is actually the model component, and the Danish GCS trash classification is actually the inference component. So it has been successfully deployed, as you can see by the healthy status. It has been successfully deployed to the Danish GCS core. right? In order to illustrate the communication between the core device and also the Danish garbage bin, I have actually created the Ubuntu virtual machine for both of them. So first of all is the Danish green grass core. It's a Ubuntu virtual machine, and the Danish garbage one also got. So let us demonstrate. First of all, in order to demonstrate that, demonstrate the inference communication, how the client device able to send the inference request. First of all, we're actually going to display the log. We're going to display the log of the inference component. So this is the initial log. And then in the client, in the garbage bin virtual machine, we're actually going to use this command to perform the inference, this pub sub to core device. Okay, so before that, bear in mind that we actually have to activate the Python virtual environment. It's actually stated in the documentation. Assuming that you already done that, so we actually run this command. So what happened is, first of all, they established the connection. You can definitely pause to take a look at the log. Okay, so right now, at first, they actually try to publish the message. And later on, they actually try to able to receive the inference response here. So if you take a look on the core device, the same thing also happened at here. You can take a you can pause and take a look up. So let's take a look on the log for the client device. So we actually directly for this file, they straight away send 15 inference requests. As a result, we also receive 15 inference response. So let's take a look on one of it. It's actually 12. Okay, so first of all, is they actually publish the message to this MQTT topic, right? And then the core device, they will actually receive the message and they will perform the inference, and then they will actually send the inference response back to the specified topic. In this case, the Danish garbage bin that actually will receive the inference response from this MQTT topic. So here, this log actually able to prove that the inference, both the inference request and the inference response are successful. And also, you also can take a look on the logs of the Danish. You can take a look of the logs of the Danish trash classification component. Also, it has been successful. So right now, let's take a look on another one. So previously, we also mentioned that they're also able to send the IoT data every day to perform the analytics, right? So in order to do so, we actually have to use, before that, we actually have to, first of all, we have to display the data ingestion log. So in this case, the component name for the data ingestion is the Danish GCS telemetry ingestion. So we're gonna use this command to display the log in real time. So this is the initial log. Oh, bear in mind, before we actually publish the field level telemetry, talking about the device table initially is actually empty, right? As you can see right here, it's actually empty. So when you actually run this command to actually publish the field level telemetry, assuming that this is published on an hourly basis. So we run this command, and they will start to establish a connection. Okay, after the connection is successful, they will start to publish all of the message. Okay, so you can read one of it. They publish the message to the topic right here. So not only, as we mentioned earlier, not only publish to the device table, and also they also publish the IoT analytics. So as you can see right here, they also they also have right now they actually start to process the message. So it might take a while. Let's take a look for the cloud side. If you reload again, you see that it actually able to the AWS IoT rules engine able to actually receive the message, and then they actually write the latest device states to the devices table, right? So you can see this is the latest field level, and this is the timestamp. It's a UTC timestamp. Okay, and then on the other hand, the second destination is actually they're actually going to send to the AWS IoT analytics. So it actually gonna take some time for it to able to send to the AWS channel. So here's an example. So as you can see that it actually able to receive a total of 75 messages. Okay, and after that, as soon as the data has been received at the channel, they will actually the pipeline will actually pre-process the data, and then they will actually store into the data set. So this is the data set name. This is the name of the data set. And then after that, the business stakeholder can actually load the data set into the QuickSight, as you can see right here. Yeah, they can load into the AWS QuickSight, and then they can start the analysis. So this is the end of the demo, and thank you for hearing our presentation.